F4. So VW Banach and T from V to W linear such that F composed with T from V to R is continuous for all F in W star. So you take any F in W star, T takes from V to W and then you apply F, so you get a linear functional noun. So F composed with T is a linear functional. Show that T is continuous. So we will try to use the closed graph theorem. So let us take Xn converging to X in V and Txn converging to some Y in W. So to show Y equals Tx. So this is what we want to show. Then the graph is closed and then we will apply closed graph theorem. Okay, then we can apply the closed graph theorem. Okay, so now we know that F composed, so for all F in W star, we have Ftn, Ft xn. So this is F composed with T acting on xn is F of T of xn. T of xn goes to Y, so this goes to F of Y. But xn goes to x, so you have, this is also equal to, so F composed with T of xn goes to F composed with T of x. So F of T of x equals Fy for all F in W star. And since we know that the dual separates points, so dual separates points by the Hahn-Banach theorem, so this implies that Tx equals 1. So by the closed graph theorem. So you see how easily we can use the closed graph theorem. Okay. So this is another nice exercise again. So V is Banach and A from V cross V to R is a continuous bilinear form such that for all x not equal to 0, A of xx is strictly positive. T from V to V such that for all x y in V we have A of Txy equals A of x ty. So this implies T continuous. So you see here we have a completely algebraic statement. There is no convergence, no analysis, no continuity, nothing is said. We have a bilinear form and with respect to the bilinear form T is symmetric. So this is purely algebraic statement and we are going to deduce the continuity. Now just a word about what is a continuous bilinear form. That means A of xy is less than or equal to m times norm x norm y, and then so if you fix one variable then it's continuous in the other variable. That's what this tells you. And then yeah, so and A of xx is strictly, and bilinear means linear in each variable, that's all. Okay, so now again we are going to try to use the closed graph theorem. So solution, so xn goes to x and let us assume that Txn goes to y. So let z belong to V. So then you have A of Txn z equals a of xn tz. So now you pass to the limit. So it is linear in each variable, and because of the continuity condition, it is continuous when the second variable is each variable is fixed. Txn goes to y, so this goes to a of yz, and this goes to a of x tz. So these two are equal, and then this is equal to a of txz by the given condition. Okay, a of x tz is a of txz. So you have that a of y minus tx z equal to 0 for all z. So you take z equals y minus tx. So you get a of y minus tx equal to 0, and this is possible only if y equals tx. Because if it were not 0, this will be strictly positive. So that is the given condition, and therefore by the CGT we have that T is continuous. Okay. 6. Okay. So let x, y, z be Banach, and T a continuous linear operator from x to z, and a continuous linear operator from y to z. For every x in x, assume there exists a unique y in y such that ay equals tx. So you have x here, you have y here. So here I have a map from each of them into z. So x to z is t, and a to y to z is a. So for given any x, I bring tx here, and then that should be equal to ay. And then I define b. So define b from x to y given by bx equal to y. Then b belongs to L xy. B is a continuous linear operator. So B is linear, that's all, no problem. So we will just have to show continuity. Okay. So again we are going to use the closed graph theorem, one more application. So xn goes to x, and then you have bxn goes to y. So xn goes to x, so txn goes to tx, and a of bxn will go to ay. Okay, but what do you know? A of bxn by definition is equal to txn. That is how b was defined. A of bx, ay equals tx. So bxn this. So bxn goes to ay. So this implies that ay equal to tx, and by uniqueness this implies that y equals bx. Yeah, and that is exactly what we want to know. So by the closed graph theorem we have b is continuous. So you can lift the map and that becomes continuous. We saw in the lectures about right inverses, and we proved a theorem about complemented spaces and the right inverse. Okay, the kernel is complemented. Kernel was complemented. That's what we saw. Okay, so now we have VW Banach and T in LVW. So S is a left inverse means S belongs to L of WV, and now you have S composed with T is the identity in V. Okay, so this is left in previously it was T composed with S identity in W, that is the right inverse. Now the inverse lives on the left, and so this is called a left inverse. Okay, so T has a left inverse if and only if T is injective, that is 1 to 1, T injective, and range of A is closed and complemented. In W. Okay, so these are necessary and sufficient conditions for existence of a left inverse. So, solution. Let us prove one way. So, we assume that T has a left inverse. So, S exists. Okay. So, Tx equal to 0 implies x which is equal to S of Tx, because S of T is identity in V, and that is equal to 0. Therefore, T is injective. So, if you have a left inverse, automatically the mapping has to be injective. Okay, so now we let us take norm xv. This is equal to norm of S Tx V. S is continuous, so this is less than norm x, norm S times norm Tx in W. Okay, so we have norm xv less than a constant times norm Txw, and we saw yesterday in one of the theorems, if you have a bounded below, then automatically range of T is closed. Why you take any sequence in the range of T which converges, that sequence is Cauchy here, which means Xn is also Cauchy, and by continuity you will be able to complete the proof. Okay, so range of T is closed whenever you have bounded below. Okay, so that is automatic. So we have shown that T is injective, range is closed. Now we want to show that the range is complemented. So let us take N equals kernel of S. So S is a continuous linear operator, so this is closed. Okay. So let us assume that Y belongs to range of T intersection N. Okay. So this means Y equals some Tx, and then S of Y equal to 0. So S of Y is S of Tx, which is x, and that is 0, and this implies that Y equals 0. Okay. Therefore, range of T intersection N is just the singleton. Okay. Now if you take Y minus T of Sy and apply S to this, so this you get Sy minus St, which is identity, times Sy, so this is 0, and therefore Y minus T of Sy belongs to N. Okay, and this belongs to range of T, and therefore you have shown that W is range of T direct sum N. So it is complemented as well. Okay, so now for the converse. So T injective and range of T closed and complemented. Okay. So you can take W will be some range of A, direct sum n enclosed. Okay. So now you have P, W is a complement direct sum of two closed subspaces. Then by the open mapping theorem, we have that W to RA projection is continuous. This is a consequence of the open mapping theorem. We have already seen this. Okay. So then if you take so we want to define S of y. So you take y in W and you define S of y equals okay. So you take Py belongs to range of not range of A but range of T. I hope I haven't confused the earlier page. Everything is T only. Okay, fine. Range of T. So now if you take P of y that belongs to range of T, so P of y equals Tx and x is uniquely defined because we have T is injective. Okay, so P of y is in the range, so it has to be some T of x. So you define S of y equal to x. Okay. So well defined. So if you take T S of Ty, S of Tx, then Tx is already in the range, so trivially this has to be only x. So S composed with T is identity in V. And now you have W and you have V and you have range of T. This is closed, so all three are Banach spaces. And from W to R of T you have a map P, and from V to R of T you have the map T, and then you have defined the map S is a unique x such that Tx equals Py, and that's exactly the previous problem. So by previous exercise we have S is continuous and therefore we have done. Eight VW Banach and T in LVW on 2. Show that T is bijective if and only if there exists a C positive such that norm V is less than or equal to C times norm TV for every V in V. Okay. So again, so the bijection if and only if it is bounded below. So one way, so this is obvious because if you have such an inequality then automatically T is injective, so obvious, and T is already surjective and therefore you have that it is a bijection. Okay, so conversely T is a bijection. If T is a bijection Then you have T from V to W, 1 1 on 2 and linear, and it is 1 1 on 2 continuous linear. So this implies by the open mapping theorem this is an isomorphism. Okay, so open mapping theorem. That means T inverse is continuous, and that's exactly saying that norm V is less than or equal to C times norm T. That is just the condition for T inverse. You write T inverse of T inverse of TV is V, and therefore you have the continuity tells you that this is particularly true. So this is proved. Okay. Then 9 VW Banach A from dA contained in V into W closed operator. That means the graph is closed. Let B belong to LVW. It's a usual continuous linear operator. Okay. Then you can define A plus B again from the domain of A, because A is defined, B is defined everywhere. So A plus B is defined here, contained in V, taking values in W. So show that A plus B is closed. Okay. So what do you mean? Closed means let Xn belong to dA and A plus Bxn converge to some Y. So to show X belong X, so Xn going to X. So X belongs to dA and A plus Bx equal to. So these are the two conditions we have to show. Okay. So Axn plus Bxn converges to Y, but B is continuous, so Bxn converges to Bx. Therefore Axn converges to Y minus Bx, and Xn converges to X. So A is closed given. So this implies X belongs to D of A and Ax equals Y minus Bx, and therefore A plus Bx equal to 1. So this shows that this. Okay, thank you.